So far we've just looked at continuous fields in the 2D case, but now let's look at discrete physical fields in the two-dimensional case and then shortly in the three-dimensional case. This is important because if we want to look at things like molecules or atoms, then it's really useful to be able to represent these things as discrete point clouds, so the atomic nuclei at given points in space. And the subject of the tensor field networks paper is actually three-dimensional point clouds, so it's a really good time to go back into the discrete regime and see how the algebra looks. Now, in order to do this, I do need to rejig the algebra a little bit. So I've been using this vector p to point to the center of the kernel, and then the vector p prime that points from the end of p to the various points within the kernel. But in order to now align with the convention used in the tensor field networks paper, I need to reverse that kernel offset vector. So I'm using the notation RA, which points from the global origin to the center of the kernel, and then another vector RB, which points from a given reference point to the center of the kernel rather than from the center of the kernel. That's ultimately a bit annoying, but it's a pretty harmless change, and it doesn't really change the effect of doing the convolution that way. The other change to bear in mind, and I'll display the equation here, is that obviously now we're doing a sum over a discrete set of points rather than an integral. So rather than defining a continuous region of space over which we're doing the integral, we're now just going to define a set of points that get included in that convolution. And I'm denoting that with this set S here, where B is just an index that refers to any one of those points that falls within the set S of points which fall within the kernel footprint. The kernel itself still remains a continuous function, but there's no mystery there because although the physical field is now represented as a discrete set of points, in order to do the convolution, we just evaluate the kernel at each point. So it's as if the kernel were discretized as well. So you can see now we're also starting to approach an equation that looks a bit like equation 3 in tensor field networks, and that's kind of the point. So just a quick aside, if you feel like we've come quite a long way since the vanilla convolutional neural network, in a way we haven't, because the convolutions that we're doing now are really very, very similar to the convolutions in the CNN. Of course, we are now talking about higher rank features, but in terms of it just being convolutions on, on point clouds, there's not much that's particularly different from the CNN case. The fact that the points are in a regular grid in a CNN is really neither here nor there. So I hope that sheds some light on that. Incidentally, this would be a very good segue into graph neural networks and graph convolutions, generally speaking, because as I mentioned earlier, CNNs are just a special case of graph neural networks. But I think that's probably a discussion for another day. So in order to go into 3D then, we're going to define our convolutional kernel again as a separable product of a radial component times an angular component. But now, because we're working in 3 dimensions, we need spherical harmonics rather than these two-dimensional circular harmonics in the SO2 representation that we were using before. The algebra is substantially more complicated in the 3-dimensional case. The main change is that we now need to use 2 indices to refer to each irrep. So there's L, which is the main spherical harmonic index, and then within a given value of L, there's a range of m values, as is standard for spherical harmonics. Let's take a look at the Clebsch Gordan coefficients, because that's the other main complication that we need to account for. So in SO2, the Clebsch Gordan coefficients were just a simple selection rule, which stated that the m value of the kernel plus the m value of the field gives you the m value of the feature map, so they just add up. Well, that's still true in SO3, but we also now need to deal with the L values. So the key complication is this. For a given pair of L values, so you have an L value for the spherical harmonic of the field and another L value for the spherical harmonic in the kernel. For that given pair, you then get a range of possible output values, and that range of output values is given by this triangle inequality here. So the Clebsch Gordan coefficients are doing quite a lot more work in this case, but ultimately it is still just all about working out which irrep couplings contribute to the final feature map. And it's worth mentioning that in the SO2 case, we were able to express our physical field and our kernel in purely SO2 irreps. And that is also true in the three-dimensional case. So while the algebra is more complicated, conceptually it's not much of a big leap. Like in the two-dimensional case with SO2, we had SO2 irreps for the physical field, SO2 irreps for the kernel, and correspondingly SO2 irreps for the feature map, all indexed by their own spin values m. Now we have indices L and m because in SO3 you need to use spherical harmonics, and spherical harmonics are specified with those two indices. So that's why on the left-hand side for the convolutional layer definition you see the indices L0 and M0, and they just correspond to the SO3 irrep that we obtain in the feature map. The other indices A and C, well, they just correspond to, so A just corresponds to which point the convolution is being done on, and C just refers to the radial index, because those radial functions don't really get involved with the convolution, and we still need to carry that index over in order to say which radial filter was used when doing the convolution. Now, this isn't actually an SO3 equivariant convolution, it's an E3 equivariant convolution, because I haven't explained it here, but the translational equivariance and the permutation equivariance of this particular convolution is very easy to demonstrate. So that's something you can read for yourself, and I hope with that you're home and dry.